Okay, so today is the second session of this course about Burnside type result for fusion category. So for people who did not scan the QR code yesterday, you can do it now. So I give you few seconds to do that. So I hope it's okay. So yesterday we started. We explained our starting point was representation theory of finite group. In fact, character theory. So we provided few character table and we made some observation related to some zero appearing in the row where the degree is non-1. And we said that this was generalized by William Burnside. So it's true for every group that if a row of degree different from 1 has a 0 and 2. People try to generalize, to dualize that by considering the column instead of row, but you need to characterize generalization of degree different from 1. Okay, and so people generalize the usual Burnside result to any weakly integral fusion category. So this was done for any weakly integral fusion category. The example above is a specific case. RefG is a specific case of weakly integral fusion category. So it was first done in the modular case and then in general. Okay. So the goal of the course is to extend such result to a large class of fusion ring and more generally to hypergroup. And we explain the motivation for hypergroup. So the use of hypergroup may be a bit complicated, but we explain there are two reasons why we use that. First, the statement of the generalization of Burnside result for fusion ring involve, or even for fusion category, involve taking the dual of the fusion ring or the dual of the Grothendieck ring. But this dual is not a fusion ring in general. So it's an hypergroup. So it makes sense to for this point to consider hypergroup. And for another point is that hypergroup is closed under duality. So you can state the Burnside result for the dual hypergroup, and you get a dual Burnside result. So that's why we will define, we will have a Burnside property or dual Burnside property. And in fact, so every group has have a Burnside property, but not every group has dual Burnside property. We will show example of, in fact, most of the simple group has dual Burnside property, except few alternating group and 2 sporadic group. Otherwise, they are all dual Burnside. But we will mention that when we will talk about dual Burnside more specific. So then we define what is an hypergroup. So you have an algebra with a basis, and the coefficients are complex. And so you have a finite dimensional algebra with a basis and a star structure on the basis. And we want these 2 conditions on the coefficient we explained yesterday. So it's a generalization of the notion of fusion ring, because to have a fusion ring, we need these 2 extra assumptions. So the coefficient should be a non-negative integer, and this should be 1. So it's much more restrictive. Okay, so yeah, then we explain several definitions: symmetric, normalized. So we will use normalized, in fact, in the coming what we will say now, real, rational, etc. So in fact, real, rational, real, negative is everything about the coefficients, which are real, rational, non-negative, and abelian, as you can expect. So we may use this kind of abbreviation, abelian, real, non-negative. So real, non-negative hypergroup are sometimes called the table algebra. Okay. So you consider a normalized hypergroup. So this sum is equal to 1 for all C. For all AB, sorry, this sum over C is equal to 1. And you consider this linear mapping every standard element to 1. And we saw yesterday that this is in fact it's a linear map, but it's an algebra map for some trivial reason, in fact, explained here. We just need linearity, the definition of that, and the fact it is normalized, and you get directly that mu0 AB equal mu0 A, mu0 B. So this map may be called in the future an augmentation map. Okay. And yesterday we finished here. So the star structure, where is it? Here, the star structure in the definition of a hypergroup, in fact, provide a star structure, the dual structure provides a star structure on the finite dimensional algebra. So it's a finite dimensional star algebra, so it is semi-simple. So it is semi-simple, then it decomposes into matrix algebra. Okay. So I finished yesterday here. So let me continue. So each block of this decomposition correspond to a central primitive idempotent, as I expected yesterday. You have H can be represented as a block like that, and the identity on this block at 0 everywhere is central primitive idempotent. So each block corresponds to a central primitive idempotent denoted Fi in H. And if you like, without going to the specific details of this definition, central mean involving, so at the level of block, you cannot break the block. At the level of blocks, primitive mean one block, and in fact, if you have just primitive but not central, I don't know if it is not semi-simple, you have the notion of indecomposable. But here, it's semi-simple, so you don't need to care. It's just one block. And idempotent mean A square equal. So in fact, it is Fi is just identity on its block and 0 everywhere. And 0 everywhere. So something like that. 1 and then 0. Okay. Okay. So now, this is a a very general statement about finite dimensional star algebra. So now let's come back to our hypergroup. So we will consider, in fact, a normalized hypergroup because we will use this. If H is normalized, then H is isomorphic to care of mu0, care of mu0 as an algebra. So this is a well-known result at the vector space level. You have a map, a linear map, and you can it's a finite dimensional as algebra because it is normalized. And because it is normalized, the map mu0 is an algebra map. Because mu0 is an algebra map. Okay, then so where is so H? This is one-dimensional, trivially, by some linear, because mu0 map to C. Where is it? Map to C. So the kernel, the quotient is one-dimensional. It's one-dimensional, so it must be a block. So it must be a block. So you have something one-dimensional. So it cannot decompose into something smaller in this. So it should be a block. So that should exist a coefficient I for this specific block. And we will choose I equals 0. It's a choice. But this is one-dimensional, so it must be a block. Say the block for I equals 0. So H care of is equal to C. Is equal, yeah. We can identify, in fact. It's an isomorphism, but we identify. So I will write equal F0 because it's one-dimensional, and F0 is the identity of this one-dimensional space. Okay, the central idempotent. Okay, so F0 is central idempotent as above. Central primitive idempotent as above. In fact, in the paper we did not write all these details. In fact, we just wrote let F0 be the primitive central idempotent corresponding to mu0. So we skip and we did not even prove that. So we skip every. So for people who are comfortable with basic algebra or something like that, maybe it's okay. But if you're so familiar with that, it makes no too much sense to say that let F0 be the primitive linear, primitive central idempotent corresponding to mu0. That requires some more explanation. So I gave this explanation here. Okay. Okay. So just for information, even if it will not be so much useful for this introduction part, but in the rest of the course of the paper, this specific central primitive idempotent will be called mu HB, lambda HB, or just lambda H. In fact, in this work, there is an issue about the notation. There are too much notation. So the challenge is to simplify as much as possible the notation. So it's not clear to me that it's really required to use another notation for that. We can just use F0, but sometimes it will be more convenient to use that, or I don't. But it may produce some confusion if you have too much notation. Anyway. Yeah, just to note that we will provide, in fact, an explicit formula for this idempotent in section 2. We will give an explicit formula for this, for it, in the next section. Anyway. Just to have an intuition of what we are talking about here, this one-dimensional thing. In fact, when you consider group, what we are talking about, this one-dimensional thing, corresponds to the first column. You have 1 here, size 1. The first column, the size is always 1. And in fact, the decomposition, let me check. So it is the first column or the first row? I'm confused. Yeah. So here, if you consider that, the fusion ring here, it is of rank 5. So it is, for a group, in fact, the fusion ring is always commutative. So it's like if you have a commutative fusion ring, an abelian hypergroup. And in fact, it decomposes into, here, you have 5, direct sum of 5 one-dimensional. So when I said size is 1 here, this does not correspond to the dimension of the block. In fact, in this case, the block are always 1 dimensional. But in fact, what we are talking about, F0 corresponds to the first block. Okay, so this is the generalization of the first column of a character table. This is what we are talking about here. This F0 is a projection generalizing the first column of the character table. Okay. So it makes things more concrete. Okay, so now definition. So I add this definition here, even if it is not in the introduction, because in the introduction we talk about that H integral hypergroup without defining it. So a hypergroup is called H integral if 1 over n I star 1 is an integer for all I, or for all, maybe we can just write like that, A1 for all A in the basis. Because this is the notation we use. So let me add that. Okay. And in fact, this in the rest of the paper, that may be called HA. In fact, because let me write it like that. In the main content, the basis will be equal AI, and 1 over n A. So no, like that, in fact. N AI AJ AK will be denoted Nij K, and N AI star. So here it's AI star 1 will be denoted HI. And here it's AI star. Anyway, so we have the coefficient of 1 for the multiplication A and S star, and you take the inverse. And this is what we will call this coefficient. So each hypergroup is H integral if all these coefficients are integer. And in fact, this notion is not true in general for fusion ring, but we will see. In fact, I will state that just now. In fact, this is true for a Grothendieck ring of weakly integral fusion category. It's always H integral, but for a general weakly integral fusion ring, it's not always H integral. And in fact, the Burnside results we will prove require this H integral assumption. So because H integral is always satisfied the categorical level, in some sense, what was proved at the level of category, in fact, now is proved at the level of ring. The statement is no more proper to category. In fact, it's something about algebra and ring. The main point is to be H integral. So in fact, this notion of H integral can be used itself as a categorification criterion, because as I will write now, as I said, it's true in the categorical framework, but not in general. Okay. So a fusion ring whose so fusion ring. So when I say H integral, in fact, it was not correct. It's the dual which is H integral. A fusion ring R whose dual hypergroup is H integral. So correct what I said before when I said H integral is the dual is H integral. Is always weakly integral. So you take a fusion ring, and if its dual is H integral, then this fusion ring is H integral. Is always H integral. Is always a weakly integral. Sorry. It's always weakly integral. So remember, weakly integral means the global Frobenius per dimension is an integer. Yeah. Frobenius per dimension R is an integer. So you start from a fusion ring. You assume its dual hypergroup is H integral. This implies this fusion ring is weakly integral. But the converse is not true. The converse is false in general. But true for the Grothendieck ring of a weakly integral fusion category. In fact, this is that's why this is very, very interesting notion. So this property is always true at the categorical for the dual. This is always true at the categorical level. And in fact, it's very easy, in fact, to compute that. You have a fusion ring, you can very easily check that. So it is a categorification criterion. So dual H integral, dual H integral can be used as a categorification criterion for fusion ring. Let me write something. H integral as okay. Okay. The H integral can be used as okay. Now, we will state the Burnside result. One version of the Burnside result, in fact. So for commutative fusion ring, and in fact, during the course, we will state something a little bit more general at the level of hypergroup. So the first main result of this paper is the following. For this paper in this course, I cover a paper, but I should write the course of this course is the following. Generalization of Burnside result. Theorem. 1, 2. So let H be a commutative fusion ring. Commutative fusion ring. So it is the notation we use for hypergroup, but in fact, you can. A fusion ring is a specific hypergroup, so you can just consider that as a commutative fusion. With H integral dual, with H integral dual, so let let xi be a standard element, so element of the basis, an element of the basis, such that Frobenius parent dimension of xi is a commutative fusion ring, which is weakly integral, is different from 1. So here I use Frobenius parent dimension. We know that H integral fusion, the fusion ring with the H integral dual is weakly integral. We mentioned that before. But you can, if you remember, for people who were in the previous course, or otherwise I will state that now, a weakly integral fusion category, in fact, is pseudo-unitary. And so, which means that the categorical dimension equals the Frobenius parent dimension. So this makes sense to restrict to the Frobenius parent dimension here, even if it is for fusion ring, because for fusion ring we don't have a generic, another generic dimension, but we don't, because it's weakly integral, in fact, the dimension we want to consider is the Frobenius parent dimension. Different from 1. So this is the analogous of what we said for the group character table. The degree is not 1. Then there is, so I'm not very happy with this notation. There is no point here to write some indices or something like that. Just write, let A be a standard element of, then there is mu, so beta hat, the set of characters, such that mu A equals 0. It's not necessary to put indices here. Even if the content we will use indices, but here the indices are not required. So what is that? The set of characters mu from H to C. And by character, we mean ring algebra homomorphism. algebra homomorphism. Okay. Yeah. And this is the base. In fact, this is the basis of the dual hypergroup. Okay. So it's exactly as for the group character table. So in the character table, what we call the standard element, in fact, is so it's confusing because what we call standard element for a character table is the character of the group or an irreducible representation or a row. And what we call character here is a column in the for the character table before, correspond to the conjugacy class. So I'm sorry for this. In fact, these notation are really confusing, but it's like that. So if you want to apply this theorem in the group level for character with character table, what we call standard element are the character of the group, and what we call character here are the conjugacy classes or are the column. But in fact, the column are character. In fact, if you consider the I don't remember the name. The algebra, maybe the center, something like that. Yeah, if you consider the algebra generated by the center of the group, or let me check. So no, the algebra generated by the each conjugacy class corresponds to a block, one-dimensional block, and you have a commutative algebra, and in fact, yeah, this is a character in the sense of this algebra. Anyway, okay, so be careful about the notation. It may be confusing. Okay. So in fact, as I said, we will prove something more general at the level of hypergroup. We will in fact prove a more general version for a certain class of abelian rational normalizable hypergroup. Abelian rational normalizable hypergroup. Okay. So definition. Now we will consider the notion of group-like element. Group-like element in the basis. So group-like element in the basis correspond to a group-like element correspond to, for a character table of a group, correspond to a character of degree 1, linear character. So definition. in general. What we have here. Here it was defined at the level of fusion ring, so we just have to consider Frobenius per dimension plus 1 or not. But at the level of hypergroup, we don't use this like that. Frobenius per dimension equal 1. We for group-like element, we need to something normalized because we don't have the axiom. We don't have the axiom n a star a1 equal 1. So you need to normalize by that. So let me mention what we will define as group-like element. Definition. Or maybe I will do this after the pause, because it's almost time for the pause. The pause. We'll do that after the pause. Okay, so let me state this definition of group-like element. So this color. For an hypergroup H, an element A in B with A star divided by NI star 1 equal 1 is called a group-like element. Element of HP. A star 1. So what's the point here? You have so A star in general is the sum of n A star C, C. So you have that. So if you consider the component, when C equal 1, we want the coefficient. So let me to be when you normalize, we want to be 1, but we want also nothing else. So in the sum I wrote here, sum over C. So let me write it like that. A star equals sum for C in B, and A star C, C. In general, I will erase that in general. So here there are two properties. First, we want to be a group-like element. First, we want that to be 0, except when C equal 1, and we want and that's all in fact. And then we renormalize like that. But in fact, we can just write it like that. In other words, N A star C equal delta 1C N A star 1. This is exactly the same thing. And in fact, there is no problem division by 0, because by the definition of hypergroup, if I am not mistaken, which is, where is it? You have that. This is greater than 0. This is non-zero. So in fact, we just need a group-like element is an element A such that this is true. So this coefficient is 0 except for c equal 1, and then here we just renormalize to have 1. So to renormalize, we need to be non-zero, but by the definition of hypergroup, it is non-zero. So this is much better. Let me write that. And A star C is equal to the Kronecker delta coefficient 1C and A star 1. Okay. Now, in fact, when you wrote that, you see it's completely straightforward. The reason why, in fact, this set of group-like elements form a group. It's very easy because when you multiply, wait, what's this point? What the hell? This is not correct. There is something wrong here. Oh, no, it's okay. It's okay. No, it's okay. Because in fact, this corresponds to the inverse. When you have a group, G inverse equal the neutral element. So it's okay. So it's very easy to see that in fact, if you, we will not write into the detail here, but if you have a group-like element multiply, this is also a group-like element, because in fact, A, B star, this is just A, B star, A star. This is 1 up to a coefficient, and then A star is 1 up to a coefficient, so you have AB is also, etc., etc. So it's completely trivial. So they form so the set of group-like elements form a group, a finite group with the multiplication, from H, denoted GH. Okay. Now, definition of hypergroup. So we stated this theorem. So this theorem is not true in general for general hypergroup. So we will use this theorem to provide a definition of what we will call a Burnside hypergroup, or a hypergroup with a Burnside property. And this will correspond to a standard element which is not group-like. Okay, so definition. Definition. 1, 4. A hypergroup H as is Burns, yeah. As Burnside vanishing property. Or shortly is Burnside. It will be denoted as Burnside. Is Burnside. If the following are equivalent. So if for all standard elements, the following are equivalent. 1. There is some mu in the dual basis such that mu A is 0 and 2. The standard element A is not group-like. Is not group-like. Not group-like. Okay. So is it clear that it is the generalization of what we get in theorem 1, 2? There is. So here we have only one way. Okay, I have something to check. Here there's only one way. If it is different from 1, so if it is not group-like, then it is 0. But the definition states the other way. So if it is 0, then it should be not group-like. And in fact, I guess for a commutative fusion ring, it is clear that it should be clear that if it is 0, then it cannot be 1. Let me check. Yeah. Is it true for the character table of a group? Wait. Should be okay. Yeah. I guess it's okay. Because yeah, it should be okay. Anyway, so you have this equivalence. Okay. So in other words, up to this the other side, it should be okay. So theorem 1, 2 state that the commutative fusion ring with H integral dual is Burnside. Okay. So let me give me 1 minute if I want to check whether the so to affirm, as I said, to affirm that we need to check the other way. If it is 0, then it cannot be 1, or if it is 1, then it is not 0 here. So let me write just that. Exercise. I guess it's very easy. Need check that fpdim a equal 1 imply mu a different from 0 for all mu in B. Wait. If you reformulate this in terms of group, you have an irreducible representation, a linear character. You have a linear, one-dimensional irreducible representation. You can call that pi. So irreducible representation, which is one-dimensional. And we want to check that this, for every group element, this is always non-zero. It should be clear. Otherwise, anyway, wait. In fact, so let me just have a look to this. What do we have here? So at least for this example, it's clear that when it is 1, we don't have 0. What is ID? Why it should be true? In general, it looks like it's always a root of unity. Yeah. Because mu rho is representation. So you take here, you are considering element of the in conjugacy class. So they are of finite order. And so you have, if you take the order n is the order of G. G power n is the neutral element. But rho is a representation, so it should be 1 on the neutral element. So rho of G power n is 1, so it's a root of unity. And so the element here should be root of unity, and so cannot be 0. That's why. And that should work for general fusion, commutative fusion ring. So let me write that for a group. For the commutative fusion ring example. So this is exercise. Example. And this is exercise. Exercise. For the commutative fusion ring CH of G of character of the finite group G, so F P A equal 1 correspond to degree of the character equal 1 of character like that. But for all G in G, so which means linear character, but a linear character is a one-dimensional representation. So rho. So for all G in G, let n equal the order of G. Rho of G power n equal rho of equal 1. It's equal like that. So G is a root of unity. So is different from 0. Okay. And in fact, the a character of a character. So if you follow the notation, here you have the fusioning of character, and here we are talking about the character of the fusioning of character. In fact, it is given by one element of the group. Here with above notation. New rho equal rho of G. So more precisely, for all mu in B hat, there exists a G in G such that mu such that for all rho, mu of rho equal rho of G. And such in fact, it depends only on the it only depends on the conjugacy class. Conjugacy class of G. We have the same. Anyway, so you see why it is non-zero, and for commutative fusion ring, I guess you can write a proof along this line. Anyway, okay, so we really have that a commutative fusion ring with an H integral dual is Burnside in the sense defined here. Okay. Tac. Tac. Next. There exists, not that, there exists simple integral fusion ring which are not Burnside. There exist fusion rings which are not Burnside, but in fact, we have this simple integral fusion ring, which is useful for people who want to classify, like me, simple integral fusion category. The fact the Burnside property is a criterion making the Burnside property as an efficient categorification criterion, even for the class of simple integral fusion ring I am personally interested in. I am working on. It is my main research topic. Okay, so what is this? Let me just very quickly explain what this. I will not. Maybe I can. Let me check. It may be interesting. Maybe I can put one example here. Yeah. Let me show you, because it is interesting. So where is it? Work, LaTeX. Now I have to find the paper somewhere. Yeah. Yeah. And here. Okay, so it's an appendix. Yeah, it is. So, you see, we classified the, as I already mentioned several times. I hope it is visible here. Visible. We classify simple integral fusion ring for this range, and in fact, among this range, we found only 4 non-Burnside simple integral fusion rings, and these 4 are isotap to representation of A7. So here they are written. So what should I do? Maybe I can just put one. I will not copy and paste everything, but just one. And I will put it in the note. Okay. Tac. like that. But it is rare. Here is one example. Let me add it. Okay. Okay. Student data. So this example is isotype to this Grothendieck ring of that. So you have the category of representation of the alternating group A7. You have its Grothendieck ring, and it is of rank 9. This Frobenius parent dimension to 2520, and this type, so the Frobenius parent dimension of the basic element. It's multiplicity 1, except for this one. So you have some variation. So for this type, you can have several possible fusion rings. One of them is the Grothendieck ring of that, which is Burnside, because every group is Burnside. But some other one are, for example, this one is not Burnside, because, in fact, at the group level, the group, you can reformulate it as a group level, in fact, a fusion ring is Burnside if, for every basic element, its matrix, fusion matrix has norm 1, if and only if its determinant is non-zero. I will mention that this is important. In fact, for a commutative fusion, so commutative fusion ring is Burnside if and if for all basic element or standard element, its fusion matrix is as norm 1 if only if determinant is non-zero. As norm 1 if and only if its determinant is non-zero. And in fact, in above example, isotype of rep A5, we have the determinant of the second matrix is always plus or minus 36, but norm 6. In above example, the determinant is plus or minus 36 of the second element, of the second one, of the second matrix is plus or minus 36, but norm 6, which is non-zero. So what is the point of considering norm and determinant? This will make even more concrete this definition So group like, remember that it is Frobenius parent for as a group, as a ring level. As a fusion ring level, it corresponds to non-Frobenius parent dimension different from 1. But the Frobenius parent dimension is, by Frobenius parent theorem, it is the norm of the fusion matrix. So it means fusion matrix of norm different from 1. Okay, and then the fact that there exists this is equal to 0 because, in fact, even if you the determinant of the fusion coefficient equal to the product of the row, of the element in the row. So you have here the determinant of the fusion matrix is a product of this element, because in fact the fusion matrix is diagonalizable. In fact, this diagonal is exactly that. This is a reorganization of the diagonal. So for a commutative fusion ring, you have this kind of table in general, and you organize the diagonal of the matrix, fusion matrix, like that. And so the product of the element of the diagonal is the determinant. So you mean the determinant, the existence of a 0 in this row, or in one row, is equivalent to have a 0 determinant. Okay. So which means 0 determinant is equivalent to the matrix to be invertible. So you get something which is really funny here, is that the commutative fusion ring is Burnside if only if for all basic elements its fusion matrix is invertible if only if it corresponds to a group-like element. Norm 1. Okay. So if you consider this matrix, in fact, it has norm 6 and the norm 6 and determinant 36. So this cannot be categorified. This is very, very nice. Okay. So what next? So what I was talking about. Note this exists. So we provided an example of something which is not Burnside. Okay. So let me come back to the introduction. My note. Okay. Okay. So in more generally, yeah, in general, so it is easy to see that a hypergroup is Burnside if only if the set of invertible standard elements coincide with the set of group-like elements, as I explained for commutative fusion ring. It is easy to see that a hypergroup is Burnside if and only if the set of invertible standard elements, so invertible in the sense of the algebra, coincide the set of group-like elements. So in some sense, it is something quite natural. And it's very surprising that it's not true in general for an hypergroup or even for a fusion ring. Okay. So I realize that what I write is not very readable. I'm sorry. It is easy to check that. Anyway. Okay. Now, for the last 5 minutes, what should I do? So we will start. This was the introduction of the introduction, and now there is a new subsection, a subsection in this introduction about the dual hypergroup of a normalized hypergroup. So I mentioned the notion of normalizable, but I did not explain what is normalized. In fact, a normalized hypergroup is an hypergroup which is renormalized in such a way it is normalized to normalized weight. Okay, no, sorry. Normalized is okay. And later we will see the notion of normalizable. But it's not the point here. So normalized. Okay. So let H be an abelian normalized hypergroup. Be an abelian normalized hypergroup by the abelian assumption the dual basis form a basis for the dual of the algebra H, which then is just generated by B hat. And we can define a multiplication there on which one can define a multiplication, as I will explain now. So you consider an abelian normalized hypergroup, you consider the set of characters. Because this is abelian, this set of characters is a basis for the dual of the algebra H, which then can be written like that. And we will define the multiplication here. Here, I guess, this dual is defined as a vector space. So now we will define an algebra structure. Okay, so So first, on B hat, the multiplication is as follows. Multiplication is so the multiplication mu I denoted like that star mu j is such that mu I star mu j of A is mu I A mu j A. So it's like a kind of convolution or something like that. I guess I will have to stop now. Already time. Let me check. Yeah. For all A in B. And then extend linearly mu I mu j on the entire C of B hat. Oh, wait. No, C of B. Wait. So there are two on the entire C of B. Okay. So I have to stop now. So you define it. In fact, it is defined. This is a map. This is a form from H to C. So you can define it as what value it takes. It's a function. So this function is completely determined by all this value. So you first determine the value on the basis, and then you extend it linearly, and you get a function on all H, and this is exactly what you have an element from H to C, completely determined, and so you get in such this way a composition, multiplication on here, and then on here by linear extension again. And I have to stop now, so I stop here.